welcome to this problem walkthrough. Today, we'll be exploring problem number 776, titled Split BST. In this session, we'll dive into understanding the problem, breaking it down step by step, and analyzing potential solutions. Let's get started. The task is to split a binary search tree, or BST, into two smaller BSTs based on a given target value. You are provided with the root of the tree and an integer target. The goal is to split the tree such that one subtree contains all nodes with values less than or equal to the target, and the other contains all nodes with values greater than the target. Importantly, both resulting subtrees must maintain the properties of binary search trees. The output of this function will be a list of two elements, the roots of the left and right subtrees. The input tree will not contain duplicate values, and the constraints ensure we are working with up to 500 nodes, where node values in the target can range from -10 to the power of 9 to 10 to the power of 9. To help clarify, let's look at an example. Suppose the input tree is represented as an array 4, 2, 6, 1, 3, 5, 7, and the target value is 2. The tree structure can be visualized as having 4 as the root, with 2 and 6 as its left and right children, respectively. Below 2, we have 1 and 3, and below 6, we have 5 and 7. The task is to split this tree into two subtrees. The left subtree will contain all values less than or equal to 2, and the right subtree will contain all values greater than 2. The output will be the roots of these two subtrees. Now, when we split the tree using the target value of 2, the left subtree will consist of nodes with values less than or equal to 2, which forms the tree rooted at 2 with 1 as its child. For the right subtree, we include all values greater than 2. This forms a tree rooted at 4, with 3 as its left child and 6 as its right child. Below 6, we still have 5 and 7 as its children. The output for this example is two lists, 2, 1, for the left subtree and 4, 3, 6, null, null, 5, 7, for the right subtree. This split preserves the binary search tree properties in both subtrees. Now consider a simpler example where the input tree is just a single node with the value 1, and the target is 2. Since the only node, 1, is less than or equal to the target, the left subtree will simply be the tree containing this single node. The right subtree, however, will be empty because there are no nodes with values greater than 2. The output is therefore 1, representing the left and right subtrees respectively. This demonstrates how the function handles cases where the entire tree falls into one of the two resulting subtrees. Let's look at another example with a more complex tree. The input tree is represented by 6, 3, 8, 2, 4, null, null, 1, null, null, 5, and the target is 5. When visualized, the tree has 6 as the root, with 3 and 8 as its left and right children. Below 3, we have 2 and 4, and below 2, we have 1. Additionally, 4 has 5 as its right child. The task is to split this tree based on the target value of 5. Here's how the tree is split when the target is 5. The left subtree, which contains all nodes with values less than or equal to 5, is rooted at 3. This subtree includes 2 and 4 as its children, with 1 as a child of 2 and 5 as a child of 4. The right subtree, containing values greater than 5, is rooted at 6, with 8 as its right child. The output for this example is 3, 2, 4, 1, null, null, 5, 6, null, 8, where both resulting subtrees maintain the binary search tree structure. Finally, let's consider some constraints and edge cases. The tree will always be a valid binary search tree, and all node values are unique. The target and node values can range between -10 to the power of 9 and 10 to the power of 9. In edge cases, such as a single node tree, the output depends on whether the node's value is less than or greater than the target. For example, if the root is 1 and the target is 2, the output is 1. If all node values are less than or equal to the target, the right subtree will be empty, and similarly, if all node values are greater than the target, the left subtree will be empty. These scenarios ensure the function handles all potential inputs gracefully. To tackle the split BST problem, one approach we could consider is the brute force method. The intuition here is simple: traverse the tree and create two separate BSTs by iterating over all nodes. Nodes with values less than or equal to the target would go into one tree, while nodes with values greater than the target would go into the other. The steps involve performing an in-order traversal to get a sorted list of all nodes. After that, we split this list into two parts based on the target value and then reconstruct two new BSTs from these lists. While this method works, it has significant drawbacks. First, it requires O(n) time for traversal and another O(n) for reconstruction, resulting in an overall complexity of O(n). Additionally, it uses extra space to store the node list, and since the original tree structure is lost during reconstruction, it's an inefficient and unnecessary method for this problem. A more efficient method is the optimized recursive approach, which leverages the inherent properties of a binary search tree. Since nodes in the left subtree are smaller and those in the right subtree are larger, we can directly split the tree without reconstruction. The key observations are that if the root node's value is less than or equal to the target, it belongs in the left subtree. In this case, we recursively split the right subtree. The result of that split gives us the right subtree of the final output. Conversely, if the root value is greater than the target, the root belongs in the right subtree, and we recursively split the left subtree. This approach follows a clear set of steps. If the root is null, we return null for both trees. If the root's value is less than or equal to the target, we split the right subtree, attach the left part to the root's right child, and return the root as the left subtree. Similarly, if the root's value is greater than the target, we split the left subtree, attach the right part to the root's left child, and return the root as the right subtree. This process continues recursively until the entire tree is split. The optimized recursive approach is both time-efficient and space-efficient. The time complexity is O(h), where h is the height of the tree, as we only traverse each node once. The space complexity is also O(h), which accounts for the recursion stack. This method has several advantages. It avoids reconstructing the tree, preserving the original structure, and requires no extra space for storing nodes. These factors make it an efficient, in-place solution. The recursive approach was chosen because it directly utilizes the BST property, making it intuitive and elegant. Compared to the brute force method, it eliminates redundant traversal and reconstruction, making it faster and more memory efficient. However, like any recursive method, there is a potential trade-off. For very deep trees, the recursion stack could lead to stack overflow. This issue can be mitigated using techniques like tail recursion or converting the approach to an iterative one. On the other hand, the brute force method, while simple to understand and implement, is inefficient due to its higher time and space complexity and its failure to preserve the tree's original structure. These limitations make it less suitable for this problem. The key insight for this problem lies in recognizing the power of the BST property. By focusing on the root node's value relative to the target, we can determine the split point and handle the left and right subtrees recursively. This insight eliminates the need for additional data structures, in-order traversal, or tree reconstruction, significantly simplifying the solution. The optimized recursive approach stands out as the most effective strategy because of its efficiency and elegance. It showcases how leveraging BST-specific properties can simplify even complex tree problems. By avoiding unnecessary operations and directly working with the tree structure, this approach highlights the importance of understanding the underlying properties of the data structure being used. Overall, it's the clear choice over the brute force alternative, offering both practical and theoretical advantages in solving the split BST problem. To begin, the problem requires us to split a given binary search tree, or BST, into two separate trees based on a target value. The first tree, tree 1, should contain all nodes with values less than or equal to the target, while the second tree, tree 2, should contain all nodes with values greater than the target. Importantly, both resulting trees must preserve the BST property. One way to approach this is through a brute force method. First, we traverse the tree using an in-order traversal, which processes nodes in a left-root-right order and produces a sorted list of node values. Then, we split this sorted list into two separate lists, one for values less than or equal to the target and the other for values greater than the target. Finally, we reconstruct two new BSTs from these lists. While this approach is straightforward, it involves creating intermediate data structures and rebuilding the trees from scratch, making it less efficient. The sorted order produced by in-order traversal plays a crucial role in the brute force approach. It ensures that when we split the list into two parts based on the target value, the resulting sublists directly correspond to the desired structure of tree 1 in tree 2. Rebuilding the BSTs from these sorted sublists guarantees that both resulting trees maintain the BST property. Let's consider the time complexity of this approach. The in-order traversal takes n time, where n is the number of nodes in the tree. Splitting the sorted list also takes n, and reconstructing the two BSTs from the lists requires another n. Therefore, the overall time complexity of this method is n. As for space complexity, the traversal requires storing all nodes in a sorted list, which uses n space in memory. Now, let's analyze the data structures involved and introduce a more optimized approach. The input is the BST itself, represented as a tree of nodes where each node has a value and pointers to its left and right children. During the brute force approach, we use an intermediate sorted list of values, which takes n space. The output consists of two new BSTs, each represented in the same node pointer structure as the input. However, we can improve upon this brute force method with an optimized recursive approach that performs the split in place. This eliminates the need for intermediate lists and the overhead of reconstructing the trees. The intuition here is to directly manipulate the tree structure by recursively detaching and reattaching nodes to their respective trees. This keeps the process efficient while preserving the BST property. The recursive approach operates on the tree structure itself, significantly reducing both time and space overhead. To implement the optimized recursive approach, we use a divide and conquer strategy. The base case arises when the current node is null. In such cases, we simply return two null trees since there are no nodes to split. In the recursive case, if the current node's value is less than or equal to the target, the node belongs to tree 1. We then recursively split the right subtree into two parts. One part still belongs to tree 1, and the other becomes part of tree 2. The right child of the current node is updated to point to the subtree that remains in tree 1. Finally, we return the current node as the root of tree 1 and the other subtree as tree 2. If the current node's value is greater than the target, it belongs to tree 2. Here, we recursively split the left subtree into two parts, updating the left child of the current node to point to the subtree that stays in tree 2. This ensures that nodes are reassigned in place while maintaining the BST property. By directly manipulating the node pointers, this approach avoids the need for additional data structures like intermediate lists or rebuilding the trees entirely. Each node is reassigned to either tree 1 or tree 2 based on its value, and the BST property is preserved through recursive detachment and reattachment of subtrees. This method is highly efficient. In terms of time complexity, each node is visited exactly once, resulting in an n runtime. The space complexity is reduced to h, where h is the height of the tree, as the only additional space used is for the recursion stack. This is a significant improvement over the brute force approach, making the recursive method an ideal solution for this problem. To help visualize this, let's consider an example. Suppose we are given the following BST. The root node is 5, with 3 and 8 as its left and right children, respectively. Node 3 has 2 and 4 as its children, while node 8 has 10 as its right child. Now, if the target value is 4, we split the tree into two. Tree 1 will contain all nodes with values less than or equal to 4, forming a tree with 4 as the root, 3 as its left child, and 2 as the left child of node 3. Tree 2 will contain all nodes with values greater than 4, forming a tree with 5 as the root, 8 as its right child, and 10 as the right child of node 8. This demonstrates how the recursive approach efficiently splits the BST while preserving its structure and properties. The provided solution splits a given binary search tree, BST, into two separate subtrees based on a target value. Nodes with values less than or equal to the target are grouped into the left subtree, while nodes with values greater than the target are grouped into the right subtree. ###code explanation. TreeNode class. The TreeNode class defines the structure of each node in the BST. Each node contains a value, val, a left child pointer, left, and a right child pointer, right. Split BST function. This recursive function splits the BST into two parts. 1. If the current node, root, is none, it means we've reached the end of a subtree. In this case, we return none, since there are no nodes to process. 2. If the current node's value, root.val, is less than or equal to the target, the node belongs to the left subtree. The function recursively processes the right subtree, root.right, and splits it further. The root.right pointer is updated to point to the left part of the split result, and the current node, root, becomes the root of the left tree. 3. If the current node's value is greater than the target, the node belongs to the right subtree. The function recursively processes the left subtree, root.left, and splits it further. The root.left pointer is updated to point to the right part of the split result, and the current node, root, becomes the root of the right tree. The base case ensures that recursion stops when there are no nodes left to process. The recursive traversal ensures that the BST property is preserved in both resulting subtrees. ###key points. The algorithm runs in O, H, or H is the height of the tree, since it processes each node at most once. The function handles edge cases, such as an empty tree, root is none, or when all values are either less than or greater than the target. This solution is efficient and directly leverages the BST's properties to split the tree without additional space for traversal or reconstruction. Here we begin the implementation of the split BST problem in Java. First, we define a nested static class called treeNode to represent the structure of each node in the binary search tree. Each tree node has an integer value, as well as pointers to its left and right children. We provide two constructors, one to initialize a node with just a value, and another to initialize it with a value along with specific left and right children. Then, we define the split BST method, which takes two parameters, the root of the tree and the target value. This method will return an array of two tree nodes, representing the two resulting subtrees after the split. We start by handling the base case. If the root is null, meaning the tree is empty, we simply return an array containing two null values. Next, we check if the value at the current root node is less than or equal to the target. If it is, this indicates that the current node belongs to the left subtree. To handle nodes that belong to the left subtree, we recursively call the split BST method on the right child of the current node, as the right subtree might contain additional nodes that also fall within the left subtree after the split. The recursive call returns two subtrees, which we store in the split right array. We then update the right child of the current node to be the first subtree from split right, effectively connecting the appropriate portion of the right subtree to the current node. Finally, we return an array with the current root as the left subtree and the second subtree from split right as the right subtree. On the other hand, if the value at the root is greater than the target, the current node belongs to the right subtree. In this case, we recursively call split BST on the left child of the current node, storing the result in the split left array. We update the left child of the current node to be the second subtree from split left and return an array where the first subtree from split left becomes the left subtree, and the current root becomes the right subtree. This completes the implementation. To begin solving this problem, we start with the root node of the given BST, which has a value of 4. The target value is 2. Since 4 is greater than 2, this node will belong to the right tree. Therefore, we recursively focus on splitting the left subtree, which has the root node 2. At this point, our variables are root equals 4 and target equals 2. Now, as we move to the node with value 2, we find that it satisfies the condition 2 equals 2, meaning this node belongs to the left tree. So, we continue by recursively splitting its right subtree, which has the root node 3. Here, our variables update to root equals 2 and target equals 2. At the node with value 3, we compare it with the target value 2. Since 3 is greater than 2, this node will belong to the right tree. As a result, we proceed to split its left subtree, but the left child of this node is none. This brings us to the base case where the root is none, so we return none, none. After this, we backtrack to the node with value 3. Its left child is set to none, which represents the left split, and the node itself becomes the right split. This gives us the result, none, 3, at this step. Now, backtracking further to the node with value 2, we set its right child to none, which represents the right split, and return 2, 3, where the left subtree is rooted at 2, and the right subtree is rooted at 3. Finally, at the root node 4, we set its left child to the subtree rooted at 3, representing the right split. The final result of this split is 2, 4, where the left tree is rooted at 2, and the right tree is rooted at 4. The output of the split operation gives us two separate trees. The left tree is rooted at 2, with a structure where the left child is 1, and the right child is none. The right tree is rooted at 4, with a structure where the left child is none, and the right child is 6. This completes the split for the first example, where the target was 2. Let's now look at another example with a different target value. In the second example, the BST has a root value of 5, and the target value is also 5. Starting at the root node, we see that 5 satisfies the condition 5 equals 5, meaning this node belongs to the left tree. We then proceed to split the right subtree, which has the root node 7. Here, our variables are root equals 5 and target equals 5. At the node with value 7, we find that 7 is greater than 5, so this node belongs to the right tree. We now attempt to split its left subtree, but this subtree is none. This brings us to the base case where the root is none, so we return none, none. Backtracking to the node with value 7, we set its left child to none for the left split, and the node itself becomes the right split. The result at this step is none, 7. Returning to the root node 5, we set its right child to none to represent the right split, and we return 5, 7, where the left subtree is rooted at 5, and the right subtree is rooted at 7. The result of this split operation gives us two trees. The left tree is rooted at 5, with a structure where the left child is 3, and the right child is none. The node with value 3 has two children, 2 on the left and 4 on the right. Meanwhile, the right tree is a single node with value 7. This completes the split for the second example, where the target was 5. Now, we will move on to a third example with a higher target value. In the third example, the BST has a root value of 8, and the target value is 10. Starting at the root node, we observe that 8 satisfies the condition 8 equals 10, so it belongs to the left tree. We then proceed to split the right subtree, which has the root node 12. Here, our variables are root equals 8 and target equals 10. At the node with value 12, we find that 12 is greater than 10, so this node belongs to the right tree. Next, we attempt to split its left subtree, but this subtree is none. This is the base case, so we return none, none. Backtracking to the node with value 12, we set its left child to none for the left split, and the node itself becomes the right split. The result at this step is none, 12. Returning to the root node 8, we set its right child to none for the right split. The final result of this split is 8, 12, where the left subtree is rooted at 8, and the right subtree is rooted at 12. The output of this split operation gives us two trees. The left tree is rooted at 8, with a structure where the left child is 4, and the right child is none. The node with value 4 has two children, 2 on the left and 6 on the right. The right tree is a single node with value 12. This concludes the split for the third example, where the target was 10. With these examples, we've demonstrated how to effectively split a BST into two trees based on a target value. The time complexity of the split BST function is determined by the height of the binary search tree, or H. This is because the function performs a recursive traversal, processing the current node and deciding whether to move into the left or right subtree based on the target value. Importantly, it only traverses a single path from the root to a leaf, rather than exploring multiple branches. In the best-case scenario, a perfectly balanced tree has a height of O log n, where n is the number of nodes in the tree. This means the time complexity is O log n. However, in the worst-case scenario, when the tree is completely unbalanced, such as in a skewed tree, the height becomes O n, leading to a time complexity of O n. Each recursive call processes the current node in constant time, meaning the total time complexity is proportional to the height of the tree, or O h. The space complexity of the split BST function is also O h, where h is the height of the binary search tree. This is due to the recursive nature of the function, which relies on the recursion stack to traverse the tree. In the best-case scenario of a perfectly balanced tree, the height of the recursion stack is O log n, leading to a space complexity of O log n. On the other hand, in the worst-case scenario of a completely unbalanced or skewed tree, the height of the recursion stack becomes O n, resulting in a space complexity of O n. Since the function does not use any additional data structures or auxiliary space beyond the recursion stack, the overall space complexity is entirely determined by the stack depth. When comparing approaches, a naive or brute force solution would involve a full traversal of the tree to extract nodes into two separate subtrees. This approach would require O(n) time to visit all nodes and potentially O(n) additional space to store the resulting subtrees. In contrast, the optimized solution takes advantage of the binary search tree property to partition the tree efficiently in just one traversal along a single path. This reduces the time complexity to O(h) and eliminates the need for additional space beyond the recursion stack. For the best case of a perfectly balanced BST, both time and space complexities are O log n. In the average case, with a randomly structured tree, the complexities remain O log n. However, in the worst case of a skewed tree, the time and space complexities increase to O(n) due to the tree's height. The mathematical proof for the big O complexity of the split BST function confirms these results. Each recursive call processes one node along a single path, with the total number of recursive calls being at most h, the height of the tree. The cost of each recursive call is O(1), as it involves splitting the node and reassigning pointers. Therefore, the total time complexity is the product of the number of calls, h, and the cost per call, O(1), resulting in O(h). Similarly, the recursion stack size is proportional to the depth of recursion, which is determined by the tree's height. This leads to a space complexity of O(h), as the stack depth reflects the maximum number of recursive calls active at any given time. When working on problems like split BST, there are several common pitfalls to watch out for. First, not handling edge cases such as empty trees or single-node trees can lead to incorrect results. For instance, if the input tree is null or consists of just a root node, your code must handle these gracefully. This is why it's essential to include base cases in your implementation. Another frequent mistake is improper pointer manipulation during traversal. When modifying a tree in place, it's easy to lose track of nodes by reassigning pointers incorrectly. To avoid this, use temporary variables to store node references before making changes. Inefficient traversal is another issue, especially with recursive approaches. Recomputing the same subproblems or revisiting subtrees unnecessarily can significantly increase time complexity. Using memoization or iterative techniques can help you avoid redundant computations. Finally, some developers overlook the distinction between value-based and reference-based comparisons. For example, in tree problems where you need to compare node values rather than references, mixing these up can lead to bugs. Always double-check whether the problem requires comparing object references or just their values to ensure accuracy. Another common challenge is overlooking the output constraints or format. For example, some problems may ask for a tuple of two trees or require that the resulting trees maintain valid BST properties. Misinterpreting these requirements can result in solutions that fail test cases. To avoid this, carefully review the problem constraints and verify that your output meets the specified format. Now, when tackling tree problems in interviews, recognizing patterns is incredibly valuable. Many such problems, including tree splitting and restructuring, often rely on depth-first search combined with conditional logic. Identifying this pattern early can save you time and effort. Another important consideration is the trade-off between recursion and iteration. Recursive solutions are typically more intuitive but can lead to stack overflow for very deep trees. Iterative approaches, while more robust, require careful management of an explicit stack. Communication also plays a crucial role during interviews. Clearly explain your approach, such as how you'll handle the left and right subtrees or maintain the BST properties. Lastly, always test your solution with diverse cases, including edge cases like empty trees, highly unbalanced trees, or even trees where all nodes have the same value. This ensures your solution is robust and performs well across various scenarios. To deepen your understanding, it's helpful to explore related problems. For instance, LeetCode 95, Unique Binary Search Trees 2, involves generating all structurally unique BSTs for a given n. LeetCode 450, Delete Node in a BST, focuses on removing a node while maintaining the BST properties. LeetCode 669, Trim a Binary Search Tree, asks you to prune a BST to ensure all nodes fall within a specific range. Finally, LeetCode 617, Merge two binary trees, challenges you to combine two trees into one. These problems share similar themes and can enhance your problem-solving skills for tree-based questions. Now, considering alternative approaches, while depth-first search is often the default choice, breadth-first search can be used instead. By processing nodes level by level with a queue, you can split the tree in a structured manner. However, BFS may use more memory for wide trees compared to DFS. Another option is iterative DFS using an explicit stack. This avoids stack overflow issues common with recursion but requires careful management of the stack. Finally, in-place modification is another alternative. Instead of creating new trees, you modify the input tree directly. While this approach saves memory, it can be error-prone, especially for beginners, as it requires precise pointer management. Each approach has its trade-offs, so select the one that best suits the problem's constraints and your comfort level with implementation. Thank you for following along. Today, we covered the split BST problem, breaking it down and discussing key approaches. Remember to focus on understanding the properties of binary trees and practicing similar problems to strengthen your skills. If you enjoyed this session, please like and subscribe for more content. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!